Hello! Welcome to our Physics from the Gut video series. In this episode, we'll derive Snell's law of refraction by using the observation that light chooses the quickest path to get between 2 points. Together, let's find this quickest path as light travels from point A to point B through 2 different materials at 2 different velocities. Follow along and you'll easily be able to derive Snell's law in 2 blinks or less, and hopefully be able to recall it for a very long time. Although implicitly used, you won't need calculus. You will, however, be using an idea of vector projection that is previously developed in a video where we prove the Pythagorean theorem. Check it out if needed. This idea of vector projection is very powerful. I promise that you'll get the hang of it and then be able to perform many other problems much more easily. Please don't worry about the video length. I have carefully laid out all of the ideas for you because I want you to fully internalize everything and feel it all in your gut. And I am also trying to refract your way of thinking a bit along the way. Here's the plan. As we proceed, our version of Snell's law will more and more closely resemble its usual form. Together, we'll derive our first version of Snell's law by minimizing the duration of a trip through land and water. We'll do this by learning a lot about vector projections and distance-time trade-offs along the way. Next, we'll learn why we even bother to use normal vectors. After deriving our first version of Snell's law, they may seem completely unnecessary. And finally, we'll intuitively work in the idea of refractive indices, and the familiar form of Snell's law will emerge. And for the coup de grace, I'll coach you on how to see all of this in about the same time it takes to write down the equation. Check out the video description below. There, you'll find easy links. Click the links to jump and replay portions of this video with ease. Okay, it's time to begin. Let's get started with an analogy to light where we run on land and wade through water. Just as light rays behave, our goal is to get from point A to point B as quickly as possible. There are 2 parts to our journey. The first part is on grassy land, and the second part is through water. Now, it turns out that we can run on land twice as quickly as we can wade through the water. And for reference, there's a fence that runs along the top. Tradition alert! I am breaking with a long-standing and mind-numbing tradition of doing proofs abstractly, with variables. Instead, the new Physics from the Gut tradition generally starts off using actual numbers. We find that specific numbers are much easier to relate to. You'll soon agree how easy it is to later replace numbers with variables. Also, don't look for specific numerical distances. The neat thing here is that they don't matter. We can derive general relationships without them. That's why I don't refer to them. Also, let's not distract ourselves with trivial cases for now. Instead, let's assume that both the horizontal and vertical distances between A and B exceed 0. So, let's work together to put some bounds on our possible paths. For example, to minimize our travel time, it's pretty obvious that we should never run towards the left and or up towards the fence, since our target B is down and to the right. Also, it makes no sense to run in a curve on land, since we can always get between those points more quickly by sticking to a straight line. Ditto for the water. Makes sense, right? All of this means that our solution will always be a straight path over land, followed by another straight path through the water. A land vector, then a water vector. Can you now see that our route is completely defined by where we enter the water? Using these ideas, can you identify some region within which we must enter the water? Remember that we're trying to minimize time. Are there some entry points that are obviously bad? Pause and ponder if needed. Well, one extreme case that doesn't violate our earlier ideas is to run straight to the right on land and then cut an angle through the water. The other extreme case is to cut an angle on land and then wade straight to the right through the water. So, our actual solution, defined by our aquatic entry point, should be in this region. The region that is bounded by these 2 extreme entry points. can you see that entry points outside of this region force us to inefficiently travel upwards either on land or in the water? As you may have noticed, we're focusing on distances now. Later on, we'll use the land and water vectors to convert those distances into times and obtain a solution. A solution where we minimize total travel time. So, let's take a closer look at our first extreme case where we run directly to the right over the grass. Notice that on land, we're only covering the unavoidable horizontal distance and not covering any of the down distance away from the fence. Therefore, this solution has us running the shortest possible distance on land. But of course, that leaves us waiting the entire down distance in the water. So we're left slowly waiting the longest possible distance. Look at this again. See how much time is spent waiting at half speed? That doesn't seem like the right thing to do. But let's inspect things a bit more closely. Let's consider what happens if we nudge our aquatic entry point down just a bit. This means we'll be covering more vertical distance on the land and less in the water. We're basically adding a tiny vertical nudge vector to the original horizontal land vector to get a new nudged land vector. Simultaneously, we're subtracting that same nudge vector from the water vector to get a new, shorter nudged water vector. This means that our distance and time on land increases, while our distance and time on water decreases. So, can you see that we have a classic trade-off here? A trade-off between our land and water times as we nudge our entry point. Here's a closer look at the red nudge vector and its effect on the land and water vectors. Let's now set the stage for understanding this trade-off more precisely. To do this, we'll first need to understand a very important relationship. Let's consider how the length of our purple land vector, making some arbitrary angle theta to the boundary, is affected by adding a tiny 1-inch vertical nudge vector. Like this. So, we're looking for the difference in length between the original land vector and this new vertically extended nudge vector. So, let's start by focusing on the land vector and the tiny nudge vector. First, notice how the angle between the land vector and lines parallel to the vertical boundary are always theta regardless of where we look. These are straight lines, and the angles between them are always theta as long as we maintain their relative orientations. Even when we go to the end of our land vector, like this. And even if we extend the land and nudge vectors like that. Now, let's return to our original picture with the vectors extended and theta now drawn in as shown. The plan is to break down our nudge vector into two components. One will be parallel to our land vector, and the other will be perpendicular to it. To make this easier, let's rotate everything by theta so that our land vector is now vertical, like this. It's very important to keep in mind what we just did here. We're rotating everything by theta. An awkwardly tilted lion and fish are here to remind us. You can see how this rotation causes our vertical nudge vector to now have an angle of theta off of the vertical. Likewise, the land vector has rotated from an angle of theta with the vertical to being completely vertical. Watch carefully. Here's that rotation again. Now, let's center things and label the vectors. We now focus solely on the rotated land and nudge vectors and magnify their intersection so that we can look more closely. With this new orientation, it's easier to see that the 1-inch nudge vector can be broken down into two components, one parallel to or in the same direction as our land vector, the other one perpendicular to our land vector. Can you see yet how looking at one component at a time will simplify things? Okay. So what's the length of this parallel component? As it turns out, I have an easy way to think about this, even though it might traumatize the linguistically sensitive. Think about words like co-worker, coordinate, cooperate, commingle, And you'll definitely encounter, but probably not love this one, co-payment. All of these involve a relationship between two or more things doing something together. Likewise, cosine measures how closely two vectors line up with each other. More precisely, the cosine of the angle between two vectors indicates the fraction of one vector that moves in the same direction as the other. Moving this to the side, we see that the cosine varies from 1 when the two vectors are moving in the same direction, to less than 1 as the angle starts increasing, to 0 when we reach 90 degrees and we're going in completely unrelated directions, to -1 when they are pointed in completely opposite directions. So I don't think of cosine as adjacent over hypotenuse, even though it is. I think of it as how much the two vectors correspond with each other, or as their factor of collinearity. So, in this case, our 1-inch nudge multiplied by our fraction of correspondence, the cosine of theta, gives us our parallel length, the vertical length that is in the same direction as the land vector. Likewise, the perpendicular component has a length of the sine of theta inches, but we'll soon see that its length doesn't matter here. Now that we know their lengths, let's see how each component separately adds to the length of our original land vector. We can do this because adding the horizontal and vertical nudge components one at a time is exactly the same as adding the tiny nudge vector itself. Both ways move us between these two dots, like this. Can you see now why we can consider the effect of each component separately? Okay, let's step back to see the whole picture again. The parallel or vertical component of our nudge vector clearly increases our land vector's length by the cosine of theta. Since we're simply moving that much extra distance in the same direction as our land vector, we'll just add that in. We'll call this new combined vector our extended land vector. Please note that even though this vector goes into the water, it doesn't mean that we're running into the water. We always run on grass. This vector is just useful for illustrating how much the land vector's length has changed as a result of the nudged entry point. Here it is again, in case you missed that. But we're not done yet. We still need to add in the perpendicular component to reach the nudged entry point, the endpoint of our nudged land vector. Remembering that the nudge vector is tiny compared to our original vector, what effect do you think its perpendicular component has on the overall length? Please reflect on this for a bit. Here's a hint. If we rotate the vector without changing its length, we trace out a circle like this. Notice how our small perpendicular component always lines up with the outline of the circle. Here it is again. Now, think about what happens if we just rotate the vector a tiny bit, like this. So, what do we have to add to the land vector to obtain the slightly rotated dotted vector? Can you see it? I'll add some labels just in case your head is spinning in circles. Hopefully, you see that we're just adding the perpendicular component of the nudge vector. This tiny motion is horizontal, in other words, perpendicular to the direction of our vertical land vector. Because it's small, it almost exactly traces out the circle's path. In fact, going around in a circle can be approximated by adding many very tiny perpendicular vectors, one at a time. Like this. Do you see how the rotating vector just followed the small nudge each time? This means that adding a tiny perpendicular vector really just changes the direction, but not the overall length of the large vector. The overall length just changes by a vanishingly tiny fraction of the perpendicular vector's already tiny length. Going back to our original picture, we can see that overall, for small nudges, the length of our land vector just changes by the length of the parallel component of the nudge, or by the cosine of theta times our overall nudge length of 1. Since this tells us the difference in length between our nudged and our original land vectors, we'll call this our delta land distance. In other words, the change in our land distance due to the nudge. Naturally, if our nudge vector points in the opposite direction, then our parallel component will also point in the opposite direction, and our land vector will decrease in length by the cosine of theta, like this. Okay, to recap, we start with our land vector reaching the water at its original entry point at an angle of theta. Next, we move our entry point by a tiny 1-inch amount to here by applying a 1-inch nudge vector along the land-water boundary. This causes our land vector to change from this to this. Notice that we never travel directly along the nudge vector. The nudge just changes our entry point, the end point of our land vector. Remember that the length of the land vector only changes by the nudge component that is parallel to the land vector, or by the cosine of theta times the 1-inch nudge length. The perpendicular component of the nudge vector, though it affects the land vector's endpoint, doesn't really affect its length. Yes, I know that I haven't shown this with complete vigor, but that's because the physics from the gut way emphasizes strong intuition over more rigorous but less direct ways. Hopefully, this powerful idea makes a lot of sense. Small, parallel additions directly contribute to the length. However, small, perpendicular additions mainly just change the direction, like moving in a circle. Very, very little, basically none, of the small perpendicular component contributes to the overall length. Okay, fine. For those who know calculus and demand rigor in their life, here it is. Feel free to pause the video and read through this, but this is definitely not something I think about when I think about refraction. In fact, I never did this calculation before making this video. This formal proof isn't really that long, but it's just not that intuitive. Although it's always good to check things different ways, relying on this proof will certainly add several blinks to how long it takes to see Snell's law. And then you'll probably lose your direct connection and it won't be in your gut. And worse yet, I'll be guilty of falsely advertising 2 blinks. And nobody ever does that on YouTube. Of course not. Remember, our goal here is to really see everything at once in your mind's eye. So, with all of this under our belt, we're ready to deal directly with the problem at hand. In other words, how to get from point A to point B in the shortest total time. We'll do this by considering the situation at 5 different entry points. At each one, we'll examine the effect that a small 1-inch vertical nudge along the boundary has on our land and water distances and times. And at each point, we'll see a different trade-off between our land and water vectors when we nudge. By the end, we'll determine what the ideal time-minimizing trade-off should be and derive an equation for that. Are you ready? Okay. Do you remember that we said our ideal situation should be in between the following 2 extreme cases? The first case where we run horizontally on land, and the second case where we wade horizontally through the water instead. So, for our first entry point, we return to our first extreme case. Here, we see that our tiny downward nudge is perpendicular to our original horizontal land path. As we discussed, this is almost identical to the change we would make to our land vector if it remained the same length and traced out a small part of a circle. Like this. Therefore, this nudge adds negligibly to the land distance, and hence also adds negligibly to the time it takes us to travel on land. We can cover this extra vertical inch over land in much, much less time than it takes us to run an actual inch. Now, how much less distance do we travel through the water after this nudge? Well, if our angle is theta, we have seen that the projection of this inch onto our water vector is 1 inch times the cosine of theta. So, by nudging the aquatic entry point down 1 inch, we're reducing our distance through the water by the cosine of theta, a non-zero fraction of an inch. That fraction depends on how close the water and the vertical vectors are to being collinear. So, hopefully, you can see that nudging down 1 inch at this entry point adds a negligible fraction of an inch to the land distance, but it saves a sizable fraction of an inch in water distance. So, nudging our entry point down here is clearly desirable and reduces our overall travel time, like we originally thought. So, it looks like we should keep nudging downwards from here. In other words, our ideal time-minimizing entry point is below here. Now, let's make a similar argument for our second entry point, which is based on our second extreme path. Here, when we nudge 1 inch up, our water path increases negligibly since our upwards nudge has no component in common with our horizontal wading path to B. Mathematically, the cosine of 90 degrees is 0. Meanwhile, our land path decreases by a sizable 1 inch times the cosine of theta, where theta is now this angle instead. Let's magnify to see this more closely. Now, let's break our nudge vector into components that are parallel and perpendicular to our land vector. Clearly, there's a right angle between our two perpendicular vectors. Therefore, if our nudge length is 1 inch, then the parallel component of that nudge is the cosine of theta inches in a direction that reduces the length of our land vector. Now, this is what things look like when we rotate the land vector to a vertical orientation like we did earlier. Here it is again. Things may be a bit more obvious when the purple land vector is vertical, but picturing that rotation requires an extra mental step. So the bottom line is that from this aquatic entry point, nudging up clearly reduces our overall time. As we saw before, our ideal entry point is in between these two extremes. But where? Notice how the angles between the vectors and boundary change as we move our entry point. This, of course, changes how much our 1 inch nudge affects our land and water vector lengths. Here it is again, without the question marks. One thought, a compromise solution, might be to draw a straight line from A to B and therefore have the same boundary angle theta through land and water. If we do this, what happens to our land and water distances when we nudge down 1 inch? Pause and ponder on this for a bit. The more you can figure this out for yourself, the firmer your final grasp will be. Okay, since we have the same angle on both sides, we have the same projected nudge distance of cosine of theta inches on both land and water. So, as we learned before, if we move our entry point 1 inch down, our land distance increases by the cosine of theta inches, while our water distance decreases by the same amount. So, that's the distance trade-off at this entry point. We're reducing our water travel by the cosine of theta inches, but we're paying for it by increasing our land travel by the same amount. So, at this entry point, we're trading off a unit of water distance for a unit of land distance. Therefore, total distance remains constant after our nudge. Mathematically, we can see that this distance trade-off ratio equals 1, like this. But what does this trade-off do to our overall time? Hint, it doesn't stay the same. True, after the downward nudge, we spend more time running an extra unit on land. But we save even more time by not having to slowly wade that same distance in the water. We're running the cosine of theta inches more, but we're wading the cosine of theta inches less. Since we're running twice as fast as we wade, this saves time. The cosine of theta inches is covered more quickly on land than in water. So, moving our entry point down from here looks like a good idea. It's a good trade-off that saves us time. Now, what will a trade-off look like if the entry point is moved a bit further down? Like this. Can you see that our land and water angles have changed a bit? Let's do this again. Watch how the angles change this time. Since our angles are now different, we'll call them theta sub land and theta sub water, respectively. Well, our land path is now closer to being vertical than before since we've added more vertical distance to it. In other words, it lines up more closely with the vertical boundary. This makes the cosine of theta sub land larger. Hence, the increase in land distance due to a 1-inch nudge will be larger than before, when our angles are equal. But what about our water path? Well, that's just the opposite. After removing some vertical distance from our wading, we're less lined up with the vertical boundary than before. Nudging an inch down from here saves us less distance on water than we had saved before. The cosine of theta sub water has become smaller. So, the same nudge now increases land distance more and decreases water distance less. I hope you can see that the further down we move our entry point, the worse this trade-off gets. So, let's see, at this particular randomly chosen entry point, theta sub land equals 37 degrees and theta sub water is 51 degrees. So, our extra land nudge distance is the cosine of 37 degrees, or about 0.8 inches, while our reduced water nudge distance is the cosine of 51 degrees, or only about 0.63 inches. Dividing these gives us a land to water nudge distance ratio of about 1.27. So, we run an extra 1.27 distance units to save one wading unit. Previously, when we had equal angles, we only had to run one distance unit to save one wading unit. The distance ratio was 1. So, saving 1 unit of wading distance is getting more expensive. 1.27 units instead of 1 unit of running. Should we make our entry point lower still? Like this? Remember, at the end of the day, we're trying to save time, not distance. So, we need to convert these relative distances to relative times. Let's say that a unit of land distance takes us 1 unit of time. Then, that same unit of distance in the water will take 2 units of time. That's because we wade half as fast as we run. It takes twice as long. Therefore, our 1.27 to 1 distance ratio becomes a 1.27 to 2 time ratio, as follows. So, replacing 1 unit of wading distance with 1.27 units of running distance saves us time. 0.63 extra time units on land saves us 1 time unit in the water. Therefore, nudging even further down will continue to save us time. Notice how we converted from distance to time by multiplying the land distance by 1 and by multiplying the water distance by 2. Again, because a given distance takes twice as long in the water. Even though our total distance is increasing with this nudge, each saved unit of wading time only costs 0.63 units of running time. Can you see where I'm going with this yet? At what entry point does this trade-off stop being worthwhile? This is an excellent point to collect your thoughts and try to figure things out. As we keep nudging our entry point down, things continue to change. With each 1-inch nudge, our additional times on land keep increasing, but our time reductions in the water keep decreasing. This happens because our land angles with the vertical boundary decrease, while our corresponding water angles increase. Like this. Here it is again. So, here's the idea. We want to keep lowering our entry point as long as a downward nudge saves more time in water than it costs on land. Does that make sense? Eventually, we'll reach the critical point. At that point, when we nudge 1 more inch, we find that the additional land time exactly equals the decreased water time. Once the costs and savings of a nudge are equal times, our nudge time ratio is 1, and we have found our point. If we go any further down, we'll start paying too dearly in increased running time to justify our decreased waiting time. Remember that in this example, we're moving twice as fast on land. So, can you figure out what the ideal distance trade-off is when we do a nudge? In other words, what distance ratio corresponds to a time ratio of 1? How many units of extra land distance should we be willing to endure to save 1 unit of water distance? Okay, since we're moving twice as fast on land, a nudge that increases our land distance twice as much as it decreases our water distance doesn't change our overall time. Make sense? If we're going twice as fast on land, we can run 2 units extra on land and then wade 1 less unit in the water without changing our overall time. So, replacing 1 unit of wading water distance with 2 units of running land distance has no effect on our total time. Here, check that out again. 1 unit of water distance takes the same time as 2 units of land distance. Therefore, our ideal land-to-water nudge distance ratio is 2. Replay and think about this a bit if I'm going too fast. Please remember that stopping, rewinding, and thinking is a critical and necessary component of learning anything. And it's definitely not a perpendicular component. If you're not doing it, you're seriously selling yourself short. Alright, so what relationship between theta sub land and theta sub water is needed to accomplish this ideal 2-to-1 distance ratio? Note that we can't determine the exact angles here since I haven't provided specific horizontal and vertical distances. We're just looking for the general relationship that must exist between these 2 angles. Well, we know that the extra or reduced distance due to the 1-inch nudge is just the cosine of the angle that path makes with the vertical boundary. So, as we've seen, our extra and reduced nudge distances are just proportional to the cosine of their angles. If our velocity ratio is 2, then the nudge distance ratio, in other words our optimal trade-off, must also be 2. This implies that the ratio of our cosines must be 2. So, what does this actually look like? Well, starting from our previous entry point number 4, we continue down until we achieve our cosine ratio of 2, like this. Perhaps more intuitively, notice how the water vector covers less vertical distance per unit length than the land vector. It's better to cover more of that vertical distance on land where we move more quickly. After giving some thought and coming to terms with these ideas, this equation will hopefully make immediate sense anytime you think about it. Our optimal entry point occurs where our land path lines up twice as much as our water path with the vertical nudge, like it does here. Notice how this distance along the land path projects 2 units onto the vertical boundary. But the same distance on the water path projects only 1 vertical unit on the boundary. By symmetry, this also works in reverse. The nudge distance along the vertical boundary projects twice as much on the land path versus the water path. This is because the boundary projects onto our paths in exactly the same way as our paths project onto the boundary. So, the extra nudge time on land cancels the reduced nudge time through the water. So nudging a tiny amount from here only negligibly changes our overall travel time at this entry point. Clearly, nudging from any other entry point will have a different non-optimal cosine ratio. Doing this would put us in a land-water time trade-off that increases our overall time in one nudge direction and decreases it in the other. So, here we have the equation for a velocity ratio of 2. Can you now generalize this relationship to work for any running/waiting speed ratio? Hopefully, you can see that we only have to replace our velocity ratio of 2 with a general velocity ratio. Like this. So we made it! We're staring at our first version of Snell's law. Finally, for completeness, let's see how our formula deals with a trivial case where A and B are horizontally across from each other. As always, we seek the fastest path between A and B. Without worrying about equations, what do you think the quickest path is between these points? Okay, let's cheat and draw a straight line between them. Now it should be pretty obvious that any other path involves running up or down on land and then having to wade down or up in the water. All of that up-down motion just increases our time in both land and water. It's clearly not optimal. When we start with the horizontal path, there's no trade-off where one distance increases and the other decreases. Both distances simply increase when we move our entry point farther away from this ideal point. Hence, the shortest and quickest path in this case is just a straight line from A to B. Let's see how our formula jives with this solution. Since we're running and wading perpendicular to the water boundary, we get a distance ratio of the cosine of 90 divided by the cosine of 90, which is 0 over 0. Now, for the case where we run twice as quickly as we wade, we're supposed to be getting a ratio of 2. But how many times does 0 go into 0? Well, 1 times 0 is 0, but our desired 2 times 0 is also 0. Actually, 0 divided by 0 is a mathematical oddity. It can be equal to 1 or 2, or really anything. So the formula actually works here for a velocity ratio of 2. But, in fact, it would work for any velocity ratio. The upshot is that when we run into the water at a 90-degree angle to its boundary, then we should just continue through the water at the same 90-degree angle. And this is true regardless of what our velocity ratio happens to be. Can you see that this all makes sense? Remember that we never used our relative velocity ratio when we originally concluded that the single horizontal line was our optimal solution. We just drew the straight line and saw by inspection that it was always the shortest and hence quickest path on both sides of the boundary. So we're getting there. The formula we derived so far looks vaguely similar to the usual form of Snell's law for light. It actually is a form of Snell's law. We've really done the heavy lifting already. But to make it match the usual form of Snell's law, we'll need to work with light rays and make 2 adjustments. First, Snell's law uses angles measured with respect to the normal vector. And second, indices of refraction are used instead of velocities. Let's tackle one at a time. The normal vector is defined to be perpendicular to the boundary between the 2 materials. The common form of Snell's law requires us to measure the angle of our light rays with respect to this normal vector. We'll call this theta sub n for normal. I used to wonder why. Why do we complicate our lives and go through all that trouble? Why not just use the angle that the light ray makes with the refractive boundary directly, like we did before? It sure seems easier than having to conjure up this normal vector. The problem with using this obvious angle becomes evident when you expand your perspective and think in 3 dimensions. Think of the xy plane as being the surface of a table and the z-axis as being perpendicular to the surface, pointing vertically away from it. Here, the incident purple light ray moves along the xy plane and strikes the refractive medium whose boundary is the yz plane. Note that instead of just being a one-dimensional line, like our land-water boundary from before, the boundary here is a 2-dimensional plane. But this means that the angle between our incident light ray and the 2-dimensional boundary isn't uniquely defined. In other words, which line on our boundary, the yz plane, do we use to define the angle with the incident ray? Do we confine everything to the xy plane and use this line to measure our angle? Or how about using the z-axis instead? Or maybe some angle in between. Things aren't quite so obvious anymore, are they? Now, you may be wondering what allows us to set up things so neatly. Why can I simply declare the boundary to be the yz plane and then further insist that the incident ray is on the xy plane? Certainly, many other orientations are possible. Well, it actually turns out that we can always rotate things into this configuration. Remember that all we have here is an incident ray and a planar boundary. First, we can rotate both together so that the boundary is oriented in any way we choose. So surprise, surprise, we choose to rotate things so that the boundary lines up with the yz plane. Let's say, as an example, that after doing this rotation, our light ray enters from above the xy plane, like this. Then, by rotating everything around the x-axis, we can confine our incident light ray to the xy plane, like this. So, why didn't our boundary rotate as well? It actually would, but please convince yourself that our boundary, the yz plane, isn't affected by a rotation about the x-axis. It's still the same yz plane. That's why I don't show it rotating. So, to make things easier to visualize, we'll only consider the case where everything is already rotated into this tidy arrangement, with the incident vector on the xy plane and the refractive boundary as the yz plane, and with the two intersecting at the origin. Please pause and think about this for a bit if needed. Okay, let's set up for the next question by making our boundary more transparent and extending the x-axis. If our incident light ray is confined to the xy plane, must the refracted ray also be confined to this plane? In other words, is it possible for the refracted ray to go up or down and leave the xy plane? Well, let's see what happens if we allow the refracted ray to go above the xy plane, like this. Think about this in terms of our two light rays having to take the quickest path between these 2 points. If this isn't the quickest path, then it's illegal. From what we learned before, consider what a tiny upwards nudge to our entry point would do to our incident and refracted path lengths. The upwards nudge would add negligibly to the incident path since that nudge is perpendicular to it, or to any vector on the xy plane. Next, what effect will this nudge have on the refracted vector's length? Hopefully, you can see that its length will be reduced proportionally to the alignment between the nudge vector and our refracted vector. In other words, by an amount proportional to the cosine of this angle. Hence, nudging our entry point up from the origin decreases our overall travel time. So this combined path through the origin is not optimal and is therefore forbidden. Making this time-reducing nudge pulls our incident ray off of the xy plane. Therefore, an incident ray on the xy plane cannot be followed by a refracted ray that leaves the xy plane. Again, it's not optimal in the time-minimizing sense and is therefore forbidden. The only remaining choice is for the refracted ray to also be confined to the same xy plane. Any other refracted ray violates our principle of minimizing time. So this is most excellent. We've greatly simplified things. Both light rays are now confined to the XY plane, and we've taken the Z-axis out of the picture. This means that we can only nudge along the Y-axis. Please think about all of this for a bit. This nicely brings us back to minimizing transit times on the two-dimensional XY plane. Our three-dimensional problem is now the more familiar two-dimensional one. And we've already solved that one when we traveled through grass and water. Just like that example, the angle that we use here is the angle between our light ray and the y-axis direction of our allowed nudges. We'll call it theta sub p for parallel, since it uses the appropriate vector that is on the planar boundary and is therefore parallel to it. If we choose our angle this way, our previous formula that uses cosine still applies. In this case, the subscripts indicate the parallel angles and velocities of refractive materials 1 and 2. We're just back to finding the ideal entry point along a line boundary, the y-axis. We're seeking the point where a small nudge along a line doesn't really affect our overall time. It's interesting to note that this chosen angle, theta sub parallel, is actually the smallest possible angle. Notice how all other angles between the incident ray and the plane involve lines that go into the forbidden z direction, like this. And, as you can see, using lines that venture into this forbidden third dimension make the angle larger. Here it is again. So, we can now see that the line that we want to use on the plane to form our angle is the line that makes the smallest possible angle with our incident ray. As long as we can find that minimum angle and use it, we don't need to worry about normal vectors, and we can use our trusty cosine formula. Many times, everything will be confined to 2 dimensions and the boundary will be a simple line. In such cases, we can easily identify and use theta sub p. However, if we're confronted with a more difficult surface, it may be challenging to find theta sub p directly. This is where the normal vector comes to the rescue and becomes the easiest option. Notice how it's perpendicular to the refractive boundary right where the incident ray enters it. This normal vector has several very nice properties. First, it's unique and pretty easy to obtain. It's just perpendicular to the refractive boundary. No need to search for minimal angles. Next, the normal vector is perpendicular to our nudge line since it's perpendicular to every line in the YZ plane by definition. Recall that in this case our nudge line is along the y-axis. And finally, with our setup here, it's confined to the XY plane. So now, let's return to our original two-dimensional example, the one with grass and water. The only difference from before is that the purple rays now represent light rays instead of our physical journey through surf and turf. And to remain consistent, we'll say that light travels twice as quickly through the air over the grass than it does through the water. Remember what we want at the end of the day. We want to know how much our nudge along the land-water boundary projects onto our light rays. Like we saw before, this lets us find the point of optimal trade-off. This time around, we'll just be using normal vectors instead. When you happen to know these minimal parallel angles, let's call them theta sub parallel land and theta sub parallel water. Just use cosines like before. So, let's start off with our traditional incident parallel angle, theta sub parallel land. Now the ratio of our projected distance to our vertical nudge is just the cosine of theta sub parallel land, where this vertical length divided by this hypotenuse. Now, let's add in the normal angle. We'll call this theta sub normal land. We now complete a new right triangle. So, the sine of this normal angle is opposite over hypotenuse, or this vertical length divided by our same hypotenuse. But since these vertical lengths are equal and they're both divided by the same hypotenuse, we see that the cosine of the parallel angle equals the sine of the normal angle. Now, I don't usually go through all these mental machinations when working with the normal angle. Instead, with a bit of thought, I think it's pretty clear that the sine of the normal angle also tells us how much the incident and parallel vectors project onto one another. I hope you can see that directly for yourself, without having to think about the parallel angle each time. Of course, we have the same situation for the water side. So, if we use the normal angles instead of the parallel angles, our cosines simply switch to sines and our equation becomes this. Here it is again. Hopefully, with some practice, you can visualize this new equation in 1 or 2 blinks. Our equation still says that the ratio of our velocities equals the ratio of our nudge distance changes. Admittedly, it's a bit harder to visualize quickly when using normal angles, but I don't think it's too bad. We can still quite directly see that we're looking at the same projection ratios. So we've just worked the normal vector into our equation. We're almost home! To get the usual form of Snell's law, we just have to use refractive indices instead of velocities. So what exactly is a refractive index? The refractive index n of a material is defined as c over v. C represents the maximum speed of light which occurs in a vacuum. V is the speed or magnitude of the velocity of light through the given medium. So, let's run a few examples to get a feel for this. First, what's the refractive index of a vacuum? As just mentioned, the speed of light in a vacuum is c. This means that v equals c here, and we get a refractive index of c over c, or 1 for a vacuum. Now, let's say we have a material in which light travels more slowly, say at half the speed of light in a vacuum. What's the index of refraction for that material? Here, v equals 0.5 times c instead. So, doing the arithmetic, we get c divided by 0.5c, which equals 2. A refractive index of 2 represents the idea that light travels through this medium twice as slowly as it does through a vacuum. If it travels twice as slowly, we can also say that it takes twice as long to cover the same distance. So, the refractive index is really just a measure of the slowness of light in that medium. As you've probably already seen in class, the refractive index of glass is about 1.5. Hence, it takes light 50% longer to travel a given distance through glass than through a vacuum. So, with c as a constant and v in the denominator, the refractive index is a measure of slowness. In other words, how many times longer light takes to travel a distance through that medium instead of through a vacuum. Let's put that idea in our back pocket. Now remember that the nudge time is the change in time duration that results from a nudge. For a light ray, we'll also call this time change our delta ray time. Similarly, we'll call the corresponding change in the ray's length the delta ray length. Using this terminology, the delta ray time equals the delta ray length divided by the speed of light in that material. To help picture this, let's think in terms of units that are normally used. It's how many meters the nudged ray's length has changed, divided by how many meters light travels each second. Clearly, our time change increases with longer distance and decreases as we move faster. The numerator, our change in the ray's length, can be further broken down. As we learned, it equals the nudge length times the direction ratio between our ray and the appropriate nudge line. Remember from before that our nudge length was always a tiny length. Before, we arbitrarily set it to 1 inch for convenience. I'm hoping that you can picture this in your head now. If not, pause this video and see if you can work it out. Knowing that the ideal entry point occurs where our nudge times are equal in both materials, we have the following. Multiplying by c on both sides and rearranging a bit gives us this. Canceling out the common nudge length on both sides and recognizing that these terms are our indices of refraction, we get Snell's law. Hopefully you're convinced, but there are too many steps here to see this in 2 blinks. It's just not the physics from the gut way. It's much faster to simply realize that both of our nudge times are proportional to our nudge distance ratios and to our slownesses, if that's a word. In other words, nudge time increases when our rays and our nudges along the boundary line up more. Nudge time also increases when the material has a high index of refraction and light travels more slowly. So that's all that appears in our final equation. Each side of this equation is proportional to our nudge time. Since we're doing things the same way on both sides of the equation, the nudge length and the speed of light that convert us from Snell's law back to actual times are the same on both sides and cancel out. With some thought and practice, I'm hoping that you can see this formula in your mind's eye as quickly as you can write it down. Time changes in each medium are proportional to nudge alignment ratios and ray slownesses, and these time changes must be equal. That's all, folks. Everything we did, and I know it was quite a bit, was to prepare you for this singular moment. Soak it in for a while until you can clearly see it all at once. And I hope you agree that it's a beautiful and compelling picture. With some work, you should be able to see this in 2 blinks or less. And of course, if we use the minimum angle instead, our sines change back to cosines and we get this, which to me is a bit more intuitive. So here's a list of all the equations, modified slightly for consistency. You should try to write each of these directly without having to think about the other ones first. No memorization, just an increasing comfort with some powerful ideas. Eventually, all of this should feel as natural as riding a bike. Now, I know you haven't seen this one before, but it should make sense if you followed everything. Hopefully, this mental picture will allow you to derive Snell's law and feel its truth every time you use it. So if you're wondering why I'm so obsessed with intuition and having this direct connection with everything, please check out the final video of a series where we take the Pythagorean theorem for 6 different test drives. In this final video, I don't do any math. Instead, I get up on my soapbox and preach about why it's so important to do things from the gut. You should find that this vector projection concept will make many things you'll encounter in physics, math, and other areas faster and more intuitive. Try applying it when you run into diffraction, inclined planes, and double-slit interference, for example. No real need for geometric proofs, finding similar triangles, etc. Just a powerful idea that lets you skip many tedious steps. The tedious steps that wedge themselves in between you and a more direct understanding. Please don't forget to like this video if it helped you. Please subscribe, check out our other physics and math from the gut videos, and let me know what you think. But, most importantly, let me know if these ideas are helpful and if there are other topics you'd like me to cover. Perhaps, in the end, we can refract each other's thinking.